Okay, so hello everyone. Thank you all for being here to attend this webinar. So today we have the pleasure to have Emile Cantacuzène, who is now a postdoc at Regina in Canada. He's working now on some data from TRIUMPH, and he did his PhD at IGC Lab under the supervision of David Vernet, defended last year. And so he will be presenting today's work. So Emile, whenever you want, you can start presenting your work. And so that you know, there will for the audience, you will have time for questions at the end of this presentation. So, Emile, whenever you want.
Oh, thank you very much. Okay, so I'm gonna share my screen. So normally you can see. So thank you for inviting me and for letting me talk. So yeah, my name is Emile Cantacuzène, and I'm gonna talk about beta-delayed spectroscopy near the drip line today. So the outline is the following. First, I'll give you an introduction of beta-decay, beta-delayed particle emission, and especially neutron emission, because this is where most of my work has been conducted. Then I'll give you some results I've obtained. So on non-statistical effects in gallium-84 beta-decay. So hopefully at the end of the introduction, you will understand what this means. Then I'll talk about new methods we developed for neutron spectroscopy. So basically, we found new ways of measuring neutron energy by using detectors that were not meant for this purpose initially. And finally, I'll give you some conclusion and perspective. So what is beta-delayed neutron emission? So this is the process where you have a neutron-rich nucleus, which we call the precursor, which will undergo beta-decay. So a neutron will become a proton, and there's the emission of a beta particle, which is an electron, and an antineutrino. And so after this process, you're left with a new nucleus called the emitter nucleus, which is in an excited state. And if the excited state is high enough in energy, above a certain energy threshold, which we call Sn, then this emitter nucleus can decay via different channels, and in particular via the neutron emission channel. And of course, if there's the emission of a neutron, well, you again feed a new nucleus. This time it's called the residue or the final nucleus. And this nucleus can be in an excited energy or in the ground state, of course. And so an important quantity linked to this process is the Q beta n window. So it's basically the difference of the Q value of beta decay, so the energy available for the decay, and the neutron separation energy, Sn. And basically this gives you the available energy for the neutrons in the end. And so on the right here, I've shown part of the nuclear chart where this process can happen. The colors represent the Q beta n window, and the hotter the color, the bigger this window, and so the more probability for this process to happen. And so I've decided to show the fission fragments region, so between nickel 78 and tin 132, because as we'll see later, this is an important region where this process happens, actually. And so during this process, there are several particles that are emitted. Of course, you have an electron from the beta decay, you have gamma rays, and you have the neutron. And gamma rays and neutron are neutral particles, which make them quite difficult to detect. And I'm pretty sure most of you know how we detect gamma rays, but I'm not so sure all of you know how we detect neutrons. And because it's because it's a very difficult particle to detect. And most of my work has been to see how we can detect these neutrons and to understand what information they give us about the beta-delayed neutron emission process in general. And so an important quantity linked to the neutrons in this process is the Pn value, which is basically the probability for a neutron to be emitted after beta decay. Another important quantity linked to the neutrons is, of course, their energy, because if you're able to measure the neutron energy, well, this gives you direct information on the levels fed after beta decay or after emission of the nucleon. And basically, this gives you spectroscopic information, and this allows you to reconstruct, for example, level schemes. And we all know that level schemes is very important for many nuclear physics aspects, especially So this process is also important for other reasons. One of the main thing is the nuclear astrophysics R process, which is a process that basically explain why around half of the elements heavier than iron have been created in the universe. And I have represented the path of this process in the nuclear chart here by this purple arrow. And as you can see, it goes through the fission fragments region. And so this is why beta-delay neutron emission is important in this region, is because basically this process will happen during the R process. And so by studying this, the beta-delay neutron emission, or by measuring quantities linked to it for certain nuclei, well, basically you're helping to understand better the R process at the same time. Another important application for this process is the reactor physics, because in a nuclear reactor, which is a very neutron-dense environment, this process will happen as well, the beta-delayed neutron emission. So the an important note about this process is that you can see 3 out of the 4 fundamental forces are under like play a role in this process. You have the weak interaction with the beta decay, you have the electromagnetism with the gamma decay, and you have the strong interaction with the neutron emission. And actually this makes it quite a difficult framework to describe theoretically. And this is why up until now, up until today, there has been no unified theory for both steps of the process. And by both steps, what I mean is the beta decay in the first part and the neutron emission in the second part. We have very good theories for beta decay on one side and for neutron emission on the other side, but both of these theories don't talk to each other. They don't have a link. And this led to the consequence that there's no theory that is able to predict good quantities linked to this process. There's no theory that can predict PN values very well, or neutron energies. And probably the reason for this is that there's no unification between each step of the theories. And so before going to my own results, I'm going to take a step back in time and try to explain the different models that have existed to explain this process. So if we go back to the beginning of the 70s, this is where the first neutron energy spectra were measured for this process. So on the left here, I'm showing actually the 2 first neutron energy spectra linked to this process. So, and you can clearly see that there's a peak type of structure there. And this was quite puzzling for the physicists at the time, because they didn't expect to see this type of structure in the neutron energy spectra. And it kind of led to a big debate in the scientific community between 2 main type of models, the statistical models on one part and the microscopic models on the other part. So I'm going to first talk about statistical models. So in these models, basically, when the beta decay occurs, you feed levels above Sn, and because you're above neutron separation energy, your system is not neutron bound anymore. And one way of seeing the system is to see it as a hot liquid messy environment that is kind of governed by statistical laws. And this is what we call the compound nucleus, basically. And the main assumption of the compound nucleus is to state that the density of levels in this region is so high that basically all the levels mix between each other, and there's no the information of the nucleus structure is kind of lost. This is what we call thermalization, basically. And so you cannot say anything about structure. You can only say stuff about energy conservation. So for example, you can only know the excitation energy or the spin parity, but nothing else. And so one of the main assumptions used in the statistical models is that the beta strength function, so the function that tells you with what percentage you feed each state, has no structure. Basically, it's either constant or proportional to the density of energy. Okay, and once you have this hot, messy nuclei, basically, well, the way it will de-excite is by emitting statistical gamma rays or neutrons. And by statistical, I mean high multiplicity and low energy, meaning that most detectors will not see them because they're too low energy. And so it's maybe a bit difficult to see how this can explain the presence of peaks in the neutron energy spectra. And so there's a researcher, Hardy, that basically showed that in a paper called the pandemonium nuclei, he showed that even by using fully statistical laws and statistical decays, you could show the presence of peaks, because if you have a detector that has a limit resolution, so a non-perfect energy resolution, basically just statistical fluctuations can lead to this type of peaks in the spectra. And this is a very bold statement, because basically by saying this, he was saying that you cannot retrieve any physical quantities. There's no physical relevance to these neutron energy spectra. There's just statistical artifacts, basically. And this kind of led to a big argument in the scientific community, because it is indeed a very bold statement. And this led to an effect that you probably have heard before, called the pandemonium effect, that basically states that indeed, if you feed, if the way of the excitation when you're above Sn is fully statistical by low energy particles that you don't see in your detectors, basically it means you don't know whenever you feed levels above Sn. And that this indirectly means that you're going to have an overestimation of the feeding of levels under Sn. And so basically by putting this context, Mr. Hardy kind of said, well, you cannot do any nucleus structure by measuring neutron energy spectra. Okay, so these type of models, they have limitations. They don't predict very well what we call integrated properties. So for example, PN or half-lives, which are integrated properties, especially in the fission fragments region. There has been some experimental evidence of high feeding towards the first excited states of the final nucleus. And this is not explained by this type of model, because what rules this type of model is the phase space, and the phase space tells you that the preferred feeding is going to be to the ground state. So this is not very well explained with this type of model. And finally, another experimental evidence is that observed some structures, some types of resonances in the beta strength function that I was talking about here. Experimentally, we have seen it. And so this goes against one of the assumptions used in this type of model. This brings me to the other big type of model, which we call microscopic models, that try to incorporate nuclear structure. So in this type of model, basically, beta decay can be seen as a quasi-particle excitation between a neutron hole and a proton particle. Why? Well, because as I said, beta decay is when you have a neutron that becomes a proton. So you can see this as a quasi-particle excitation. And because of spin parity rules of beta decay, you can show there's only like 4 different types of quasi-particle excitations. And because you're in a quantum mechanics system, all these excitations can mix between each other, and you can show that this leads to the construction of resonances in the beta strength function just around the neutron separation energy, which we call Gamow-Taylor pygmy resonances. And so this type of model kind of shows that we can explain the presence of these experimentally seen structure in the beta strength function. And it is also a bit better to predict integrated properties, so PN values, for example. However, there's also limitation. The main one is that this type of model doesn't explain the neutron emission at all. It only describes the beta decay part. And even though it's better at predicting the integrated properties, it's still not perfect at all. And so what happened over time is that and the statistical models kind of prevailed, because the pandemonium effect kind of scared everyone. And so they were a bit less confident in microscopic models. There was a big lack of computational resources at the time. And to build a proper microscopic model, you kind of need a very good machine. And of course, we didn't have the technology to pursue and to produce more neutron-rich nuclei. And so this kind of halted the research on this topic at the time. And we had to wait like 30 years or more for new results in this area. And so there's a bunch of new results that I'm not going to describe all of them, but basically since the end of the 2010s up until this year, there's been a bunch of results showing some non-statistical effects for some nuclei. And by non-statistical, what I mean is evidence that experimental evidence that the statistical models fail, especially when you get closer to shell closure nuclei. So close to nickel 78, for example, or close to tin 132. And so this is why basically we wanted to probe non-statistical effects in the beta-delayed two-neutron branch of gallium-84. So up until now, I've only talked about beta-delayed one-neutron emission, but if you have a higher Q value, well, nothing stops you to have two-neutron emission, 3 or even 4-neutron emission in some very rare cases. And why did we use gallium-84? Well, it's because it's a relatively easy isotope to produce that still has a pretty high probability to emit 2 neutrons after the beta decay, and it's very close to nickel 78. So basically, it's the perfect candidate to study these non-statistical effects for this branch. And a secondary objective that I had during my research was to develop new ways of measuring neutron energy in the facility ALTO, which is where I conducted this research, because as I told you earlier, the neutron energy is also valuable information in this process. And so this led to 2 experiments, basically, where we used 2 neutron detectors. The first experiment, we used TETRA as a detector, which is a helium-3 neutron counter. And in the second experiment, we used MONSTER, which is a time-of-flight spectrometer, which allows to directly measure energy of the neutrons. And both of these experiments happened in ALTO. So in ALTO, we produce a radioactive ion beam using the ISOL method. So basically, we accelerate electrons up to 50 MeV, which are then sent on a thick uranium carbide target. This will induce photofission of the uranium, thus creating neutron-rich isotopes. The target is heated up to around 2000 degrees so that the fission fragments can escape the target. Then we send a laser on this target in order to select the atoms we want to study by ionizing them. So there's the first selection in the Z number there. Then we can send these ions to a mass separator to select them in the mass number. And finally, we have pure radioactive ion beam that can be sent onto the beta decay stations of ALTO. So currently there's 3 beta decay stations, COCO, BIDU, and TETRA, which are each used for to measure different quantities in the beta decay. And so the kind of architecture of these beta decay stations is the same for the 3 of them. The beam is collected of the experimental setup on a tape, and this tape is controlled by an automated tape system that allows to move this tape whenever we want. And basically, why do we want to move the tape is to remove the long-lived isotopes descendants that would create background in our measurements. And so by doing with this system, what we can do is collection decay cycles, where we collect the beam for some certain time, we cut the beam and we let the radioactivity we created decay. And once we are happy with this measurement, we move away this collected beam so that the long-lived descendants don't create background in our measurements. And we can repeat this cycle over and over during an experiment in order to have more and more statistics while keeping a very low background, basically. So this brings me to the first results we've obtained at ALTO. So the non-statistical effects in gallium-84 beta decay. So hopefully now you understand what this means. And so as I said, we used the detector TETRA. So TETRA is this. It's a big detector made of highly dense polyethylene in which is embedded 80 helium-3 gas cells that you can see as these rods there. And basically, when you implant the beam there at the center, you will have beta decay and neutron emission. And so when a neutron goes inside TETRA, it will undergo elastic scattering with the highly dense polyethylene. So with each scattering, the neutron will lose a little bit of energy. until reaching very low energies, which we call thermal energies. And if a neutron of that energy enters one of the helium-3 gas cells, this reaction will occur. So a neutron plus helium-3 gives a proton and a triton with some kinetic energy. And as these particles are charged, the proton and the triton, they will ionize the gas, which will create a signal, which is the signature that we counted a neutron. So this type of detector only allows to count neutrons, but the energy information is lost in the scattering process. And the very good point of this type of detector is that it has a huge efficiency. For example, TETRA has around 52% efficiency. So along with TETRA, we had two other detectors. The second detector is a plastic scintillator, very close to the collection point of the beam. And this is just a detector that allows to detect the electrons, the beta electrons, so to tag beta decay basically, and to count the number of beta decays that occurred during the measurement. And the final detector is a high purity germanium detector to measure the gamma rays, because if you want to do spectroscopy, well, you have to have a gamma ray detector, basically, to reconstruct level schemes and etc. And so what this experimental setup allowed us to do is to, well, study gallium-84 beta-delayed two-neutron emission. The way we did this is by plotting the activity of the two neutron events. So basically, we counted all the events where two neutrons were counted almost simultaneously. And we can plot this type of curve where we can clearly see that the activity grows during a collection of the beam and then decays when we stop the beam. And we can fit this curve with what we call Bateman function. And basically, this allows us to know with precision the amount of two neutron events we had during our experiment. And we can do exactly the same process for the beta detector. And so if we efficiencies of our detectors, well, with these two quantities, we can directly measure P2N, the probability to emit two neutrons after a beta decay. And we obtained this value, which is okay. It's a good measurement in itself. It was already measured once before, but it's always good to have another measurement. But what we wanted to look at is the non-statistical effects. And so we looked at the gamma rays that arrived in coincidence with these two neutron events. And this is the gamma ray spectra, and we observed a peak at this energy there, which corresponds exactly to the transition of the 2+ to the 0+. And by measuring the counts in this peak, we were able to say something. We were able to say that basically the feeding towards the ground state of the final nucleus is less than 31%. And as I told you before, statistical models predict that you have a preferred feeding towards the ground state. And here we showed that there's less than 31% feeding there. So this is a highly non-statistical effect, and this is our result. And so we found ways of, the way we explained this was by using a microscopic model. I'm not going to detail it, but basically we showed that by using nucleus structure arguments, spin parity rules, etc., with a full by using a full microscopic approach, we could show that basically with starting with the spin parity of our emitter nucleus, there's basically a preferred pathway that leads to a 2+ level, explaining very well why we observe a high feeding towards the 2+ level there. So the takeaway message from this interpretation is kind of to say, well, look, there's other ways of explaining the neutron emission process that doesn't use statistical models, that clearly use microscopic models, and that work pretty well. And so it's just an approach to say, let's try to develop new models to explain this process. So yeah, this is the result, the final result for this measurement. So now I'm going to talk about the second part of this talk, where basically, as I said, we developed new methods for neutron spectroscopy. So basically, we used detectors to measure neutron energy when it was not made for this purpose initially. So this idea kind of started with the fact that we wanted to do Monte-Carlo simulations of the TETRA because we didn't understand very well something about the efficiency. And so we thought that if we made a simulation, maybe we could understand it better. And so I started with doing a simulation with Giant 4, which is shown in the left. And then I tested another simulation with the software MCNP, which is known to deal with neutrons very well. And in the end, the MCNP simulation was more accurate. So all the analysis was made with MCNP. And the idea came up when we plotted this graph. So what this graph is in black, you can see the total efficiency of TETRA as a function of the neutron energy. So you can see that it slowly goes down as you go up in neutron energy. But the important thing to see is the colored line there. So if you look at TETRA, you can see that the geometry of TETRA is made of rings of helium-3 cells that go ALTO and that go further and further out of the collection point. So in total, there's 4 rings, and these show the efficiency of each ring as function of the energy. And you can see that as you go up and up in energy, the inner rings, so for example, the red line there, decreases, while the outer rings increase. And this means that as neutrons go high in energy, they travel deeper in the detector before getting detected. And so the idea came up with this. This kind of means that there's a correlation between ring number, and by ring number, I mean the 1, 2, 3, 4 rings that go in each layer of TETRA. There's a correlation between this and the neutron energy. And the idea was maybe we can, if we do it properly, we can, because we can measure experimentally where each neutron has been detected in which ring. So if we know this, if we do it properly, maybe we can find the neutron energy because of this correlation there. And so 2 methods were developed using this idea, which led to a publication that I very recently submitted to EPGA. And I'm going to detail one of the methods in this talk. So this method is called iterative Bayesian unfolding method. I have not came up, it's something that exists for a very long time, that has been used a lot in particle physics, and it's now used pretty often in nuclear physics as well. It's this theorem, which is this ugly formula there. And I'm going to try to explain how we use this formula in this context. So basically, Bayes' theorem allows you to, if you have an initial distribution that you don't know, linked to a final distribution that you can measure, well, basically, and you call the first distribution the distribution of causes, and the second, the one that you can measure, the distribution of effects. Basically, Bayes' theorem tells you how they are related. And in our case, what we want is the distribution of neutron energies. And this is what we don't know. And what we have is the distribution of ring numbers inside TETRA. So our effect is the ring number distribution, and our causes is the neutron energy spectrum. And so now I'm going to detail each ingredient in this formula. So the first ingredient is PEC, and it's basically the probability that given a certain cause, so given a certain energy, what is the probability that I will detect my neutron in a certain ring. And this is encoded in a response matrix, basically, that is obtained from the Monte-Carlo simulation. The second ingredient is P0C. It's basically the initial cause distribution, and this can be taken arbitrarily. And because it's an iterative process, basically, with each iteration, this P0C will be updated and get closer and closer to what we want, which is the real distribution of causes. So initially, you can take it arbitrarily. And so you have both ingredients you need to use Bayes' theorem and obtain PCE, which is basically the inverse response matrix. And by using your data, which is the ring distribution, so NE, you can fit your data with this PCE and obtain the probability of causes, PC. And then you can compare this new PC to the old PC, P0C, by a chi-square comparison. And you can input this new PC as P0C and redo the iterative process. And each time you compute the chi-square, and at some point, it will be minimized, it will stabilize, and this is where you normally know that the PC you've obtained is the real distribution of causes. And so this method was tested for various simulated distribution. So the way we tested this is by basically simulating an energy spectra that we know in our simulation, measure the ring distribution obtained with this simulation, and use this ring distribution as input in our method. And then we can compare the distribution we used as input and the output distribution and compare them. And this is what we obtained with monoenergetic distribution. So you can see that, so initially all of these colors were monoenergetic distribution. And you can clearly see that as you go higher and higher in energy, the method loses in accuracy very much. Up until around 1.5 MeV, the mean energy is pretty close to the real one, and then it starts becoming less and less accurate. And then we need to input real neutron energy spectra that were taken in literature from previous data. I numerized this data and used it as input in my simulation, and I compared the input and the output, and you can see that, okay, the spectral shape is not very well reproduced, but at least the mean energy is accurate each time, and this is very promising. It means that this correlation method kind of works, at least to measure the mean neutron energy, especially for beta-decay, beta-delayed neutron emission spectra, because most of these, they don't go above 1 MeV. And so you can see that it's in this energy region, the mean energy is quite well reproduced. So seeing that it was working pretty well with simulated data, we then used it on real data, experimental data, where we used a neutron source. We put it at the center of TETRA. We measured the neutron, the ring distribution, and we were able to use this as input in the method. And this is the comparison between the spectrum, which is shown as this black line, and the reconstructed spectrum. And you can see that the shape now is pretty well reproduced. The mean energy is different of around 400 keV, but still it shows that it's not completely off. And it makes sense that it's not very accurate because it is a higher energy spectrum. And so the conclusion of this test was that the accuracy clearly decreases with the energy, but there's a pretty good accuracy for the mean energy, and especially for spectras that are at, for beta-decay spectras, which are rarely above 1 MeV. And there is a low accuracy for the spectral shape in general. But we didn't expect it to be good because I remind you that TETRA was clearly not meant to do any of this work before. It was just there to count neutrons normally. And so the next step was to test this new methods with a real radioactive beta-delay nucleus. And this is what, so basically this led to a new experiment, the other experiment, Monster 2025, where we directly measured the neutron energy spectrum of Gallium-82, and we compared it to TETRA's prediction. And so for this new experiment, I will very rapidly describe the experimental setup, where basically it's the same. So it was in ALTO. The beam was implanted at the center of the setup. 3 germanium detectors for gamma rays, a plastic scintillator again for to detect the beta electrons, lanthanum bromide detector for high energy gamma rays. And the main part is 39 monster cells that are located at a distance of 1.55 meters from the collection point, and that are able to measure neutron energy by the time of flight method. And so this, so with this setup, we were able to obtain this figure here, which is basically the pulse shape discrimination spectrum. So it's a spectrum that allows you to discriminate the gamma rays from the neutrons, because Monster is also sensitive to gamma rays. And you can clearly see that, so the gamma rays is the big line at the bottom, and the neutrons is a tiny little bump of statistics above. So we lacked a lot of statistics because we had some problems during the experimental setup. But however, we were still able to obtain this time of flight spectrum here. This corresponds to the neutrons count. And from the time of flight, you can reconstruct the energy spectrum, which is done there. And so what you can, so the data is shown in the black dots here. And the comparison to the TETRA prediction is the pink distribution behind. And you can see that there's a clear match, at least in the energy region overlined in gray here, and that the mean energy is also very close between both. You can also see that under around 300 keV, we don't have any data anymore, and this is because Monster has an energy threshold of around 280 keV, meaning that we probably lose a lot of the neutrons because of this. But this clearly shows that TETRA prediction are also accurate for online data, and this is very, very good. In order to show that we were probably missing a lot of the neutrons, we measured the PN value with Monster, and we have plus or minus 5%. And if you compare it with the literature value, which is very well known to, and which is 22.7%, we can clearly see that we missed at least half of the neutrons there. But we can still compare it in this region, and it works quite well. So basically, that's the end of these results. So now I'm going to conclude and give some perspectives. So we showed that the beta-delayed two-neutron branch of gallium-84 clearly shows some non-statistical effects. And we can use microscopic models to explain the neutron emission, and that work nicely. We measured for the first time the gallium-82 neutron energy spectrum, and we show that a lot of the neutron intensity is located under 280 keV. And we showed that we can use Monte-Carlo simulations to use neutron counters for neutron spectroscopy. And finally, so I'm going to give some perspective. So this is mostly what I'm doing now for my postdocs. So I'm still doing beta-decay. But this time I'm at the other side of the nuclear chart, in the proton-rich side and lower mass, and I'm looking at beta followed by particle emission as well. But this time it's either proton emission or alpha. And the way we do this is we have a cube called the RCMP detector, which is there to detect charged particles. And this cube is located at the center of the Griffin spectrometer, which is a 4 pi gamma spectrometer for beta-decay. And the reason why we want to study this, so it's for magnesium 20 and 21, it's because we can indirectly study the astrophysical hot CNO breakout sequence that links basically oxygen 15 to neon 19 and neon 19 to sodium 20 by studying the inverse process, where we have sodium 20 magnesium 20 that beta decays to sodium 20 and that emits a proton, and then that can emit an alpha to feed the oxygen 15. And this is a very preliminary spectrum of the RCMP energy spectrum. So the charged particles gated with different gamma rays, and we can see that we have a lot of statistics, and this is very promising for the future. So thank you for your attention, and if you have any question, I'll be happy to answer them.